So we left off last week, just about finishing up the Poisson distribution. So we'll do a little bit with that today, just some more examples. That way it's almost kind of like we're starting a review. And then we'll kind of transition into probably looking at some of the problems on one of those practice exams. Okay. So we've got an exam on Friday that Connect and Excel ended up originally the Excel I think was a little earlier, but because the file, there was an issue with it, I pushed that up to Wednesday. So hopefully you've started working on that before this week. If not, good luck. But I will be around if you need some help with that. This afternoon, my office hours, so usually it's 2:30 to 3:30. We'll be a little bit later today, so like 2:45 to like I'll be there close to 4, but then I have to go teach at 4. So if I'm not there right at 2:30, I probably won't be in my office until about 2:45 today. Tomorrow, typical office hours are 11 to 1. I'll also be around a lot of the day. So if those don't work for you, send me an email. We can set up a time to meet sometime tomorrow. Really, I'm pretty available throughout the entire day, kind of 9 to 5. So, feel free to send me an email if you're kind of having trouble with that and want to meet. Wednesday, we'll just continue to do review of some of those practice exam problems, just getting us ready for Friday. Other than that, it should take us up to where, get everything out of the way in terms of all the stuff we need to talk about, unless there's any questions. I'll talk a little bit about the exam. So if you have specific questions about the exam, kind of what it's going to look like, hold off on those. I will discuss that after we get through kind of this Poisson, finish up the Poisson distribution. So any other questions other than kind of the makeup of the exam maybe before we get going? Good. Okay. So I believe we left off last class, and I don't know if I remember. I don't remember what got through this yet. But basically, the Poisson distribution has this really interesting property, which is that the mean, right? We're given the average rate, right? So the Poisson was we were looking at an interval, right? We were interested in the number of successes over a certain time frame, right? Number of, I guess when we said successes, right? Whatever we're looking for. So I think the example I have to use was the number of car crashes on the road over a given week. So we've got this time interval. We have to be given what the average rate is over this interval from like historical data. So that's kind of our lambda, right? Our average rate. So the mean of the Poisson is just the average rate, right? Just lambda. Okay? So our mean is just this average rate. And a really nice property of the Poisson is the variance actually ends up also being that, right? I think I might have, we did get through, I mentioned, you can Google like Poisson variance proof and kind of see why no matter what your average rate of change is, the variance, that formula will always simplify down to just lambda. It's kind of a unique property. And then hopefully you're getting tired of me saying this for now, but right, the standard deviation would just be the square root of that, right? So, we have this really interesting property. Did we go over this atom example? I don't remember if we completely got it. I don't remember this. No, yes. We did. I thought we did. So I just wanted to make sure before I kind of glossed through it. But this was one that I showed you. I said, don't worry too much about this one because I just wanted to show you an example where we didn't have a time interval. When it comes to the exam, I'll only give you Poisson examples that are over a time interval. But we can look over kind of different intervals, like the amount of the atoms here. We can talk about how the Poisson distribution can be approximated by kind of turning that average rate of the binomial into the Poisson. Sorry, the binomial can be approximated with the Poisson. We kind of worked through that and showed how we get the exact same answer. So we'll talk a little bit about some situations just to kind of really hammer home the difference between the binomial and Poisson. We'll do one more example, and I'll do some kind of changes of the timer. So if we're thinking about which of these is not going to be a situation where we can use the Poisson, remember the real difference is with the binomial, you'll always know the maximum number of successes you can see. If I'm asking you, out of 100 coin flips, what's the probability that I see 5, right? Well, the most you could ever see is 100, right? If I'm flipping the coin 100 times, you're going to have this cap, right? Whereas the Poisson, it's going to be, how many times do I see in the next minute a coin flip come up heads? Well, you don't know how many times I can flip the coin in that minute. You don't really know what the capped number of successes are. So if we think about these examples, which one will not be able to use the Poisson distribution? The first one, we have a number of car accidents that occur on a highway on an entire day. I've used this example several times, so probably know this is going to be one to use. Really, what are we looking for? Well, we could have some average rate that happens on a day that we could get lambda for. We have this time interval of a day, right? And we're not capped. We don't know the number of possible accidents we could see, right? It kind of could go off into infinity, especially for like a bigger city. So that one seems like a pretty good one where we could apply the Poisson. What about the probability a stock exceeds 10% a given year? So just because we see a time, right, doesn't necessarily mean we can't apply. So we'll think about we're looking over a given year. What would our successes be here? Well, we're just looking at one stock and we're worried about just the number that it exceeds, right? Is it going above 10%? Is it 11%, 12, 13? That's not a number of successes, right? We're only going to see one value for what this stock return is. We're not saying something like how many stocks in the portfolio will go over 10%, right? Well, then we would have a number of stocks here. So this is going to be a situation where we can't actually apply the Poisson because there's really, we don't have a success failure defined, right? We're just looking at a value that can go anywhere from negative infinity to a positive infinity. Right? So we don't have an actual number of successes we're looking for here, so we can't really apply the Poisson. Some other situations that we could apply the Poisson to is the number of calls in a given minute at a call center. Based off of historical data, we can find the average that comes in over a minute. The successes here, just do we see a call come in, right? So do we see one call, two call? Those are our successes, right? And so we could apply the Poisson to that example. And then the last one, number of insurance claims over a month, a year, whatever our time period we're interested in is. Well, we're just thinking about, we see a claim come in, that's a success. We've got this time interval that we're looking at. We could easily apply the Poisson to this as well. So just kind of discussing some situations or some examples we might see with Poisson. We'll go through one more, which is kind of this famous example. Right? Another example where we're not necessarily looking at time, but we're looking at intervals, right? So apply it's the same kind of idea. So we've got this guy, Dist, really smart, hires a brewer by Guinness way back in the day. But he didn't have any formal statistics training or like a degree in statistics or mathematics. But as he was working at this brewery, he's like noticing these huge like silos. I call them vats. I don't know if that's what they're called. But these silos of like beer they're brewing. They have to test it, right? They want it to have a certain makeup so the beer tastes, the way they want it to. And he's noticing as they're testing this, because they can't test the entire kind of silo of beer, they have to pull out a little bit at a time. So he's testing a milliliter at a time to see, does it have a certain number of particles that we want? I think exactly what they're looking for is like yeast particles, right? So he takes out a milliliter and he kind of writes down the number of particles in that milliliter, tests another one, writes that down. Over time, he's got all this data and notices it's kind of following this Poisson distribution. Okay? So he comes up with this discovery. He also develops, we'll end up talking about the student T distributions kind of before our next exam. But none of them bear his name. So like, the normal distribution is called the Gaussian distribution sometimes because this guy Gauss discovered it. But because they have any formal statistics, they just start calling everything he comes up with like the student T distribution. Or they just refer to him. His name never actually enters the kind of equation. This is a little bit of a setup, and he made a bunch of them. But so a little bit of a setup. Think about this example. As I'm drawing out each milliliter of liquid, the milliliter becomes my interval. It's almost like that milliliter is like a week or a day. Right? So I'm not actually going to use this slide, so just sit back and listen for a second. So he keeps pulling out these milliliters and he draws this sample and he sees that in this one sample he takes, he sees an average rate of 10 particles per milliliter. Right? This is based off of the sample he's drawing out in this huge vat of liquid. So we've kind of got this average rate of 10, right? So based off the samples he's taking, the average is 10, but we're concerned because the targeted number of particles per milliliter, maybe the company wants 8, right? So just because we have this sample and we saw 10 doesn't necessarily mean that the average over the entire vat of liquid isn't necessarily 8. And so we could find something like, okay, what's the probability that in the entire vat we actually see 8 particles per milliliter, right? Same interval. Well, here if we had our Poisson distribution probability mass function in front of us, which we'll have in that formula sheet, which I'll pull open here in a second. We'll do some exam review. We'll see that all we really need is this lambda and the value x that we're interested in. Now, if I'm looking at these values, let me see which of these, probably doesn't. I mean, I can rule one of these out for sure. It's a little bit harder to know why, but which of these probably, I'm just thinking about what I'm doing. I have this average rate of 10. Well, then what's the probability I only see 8? Which of these could I rule out right away? Which one? B. Yeah, probably couldn't rule B out right away, right? D? Oh, okay. D you probably can't, right? It's unlikely, if we're thinking about what's happening here, it's just like the binomial, right? This average rate of 10 is going to have the highest probability of occurring. We know that, right? As we move away from that point, right, in any direction, we're going to see that probability of seeing that number of successes is small, right? It's declining from that average. So right away, I mean, yeah, you're right. D, like, if this is the most common outcome, we're not very far away from it. I doubt the probability is going to be that low. Theoretically, right, it could be, but it's unlikely. One of these theoretically cannot be the answer. So that's actually going to be C. Right? So let's think about why. We just said that the average rate has to be the most likely outcome. Okay? So if the probability of 8, in fact, was 0.8 something, well, we only have, right, all the probabilities have to add up to 1. So at most, the probability that 10 could be is what, 0.2, which would make it not the most likely outcome. So right away, we know that we can't see probabilities above 0.5 for anything other than that average number of successes, right? Because that has to be the most likely. If anything else has a probability over 0.5, that average rate of 10 can no longer be the most likely outcome. So right away, we can rule out C, and probably D doesn't make a lot of sense. If we're just guessing here, I'm going to throw my dart at A or B, right? But from here, it's really just a matter of plugging in these two values into our equation. So we've got our two answers, right? So we've got, our two variables that we're looking for, lambda and x. We start plugging into our equation, which gives us lambda dx, e to the negative lambda, and then x factorial. So hopefully you kind of found that factorial button on your calculator. If not, I highly suggest doing it by the time we get to the exam on Friday. But that being said, we remember what the factorial is here. I can enter this in my calculator of just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I can put that in my calculator. It's a little bit cumbersome, right? A lot easier if I know where that factorial button is in my calculator. So we can do. Okay? So we get about 0.11. Right? And that makes some sense, right? It was a value that was pretty close to that average rate. So the probability shouldn't be too low, but it also isn't going to be the highest. Right? Any questions or anything here in the process? Okay with this? I think that's all I had here. Oh, I had a great Poisson meme, which was, have you heard the joke about the Poisson distribution? It's pretty fishy. Poisson is the French word for fish. So that's what you get from my meme. So let's put this up here for a second, which is, oh, I consolidated them, so I don't have too many folders. So let's go. Yeah, I had it on here. Got a million of these files. So this is kind of our formula sheet. I would suggest one thing as we're leading up into the exam, as we start working through this practice exam in class, but also on your own. If it was me, right? I haven't given you guys a speech about the formula sheet, right? Or have I? Okay. Got so many different sections that are at different points in time. So I'm starting to get it all mixed together. But I would use this, I would print it out, and as we're working through things in class and as you're working through things on your own, start to write down next to the formulas what that formula is, right? So for instance, next to here, I would write binomial probability mass function, right? And right here, I would write weighted mean. Okay? So on the exam, I'm going to give everybody the same formula sheet. I don't have no cards or anything. So I give you all this formula sheet, but it doesn't have anything written on, right? But if you do it yourself as you're studying, as you're working through things, once you get this, it's going to be easy to picture. Like if you've been using that one you've been wrote down whatever formula was, you'll be able to kind of picture that, right? Or as soon as you get the formula sheet, what might be something you could do? Well, here's the formulas. I always forget what they mean. Really quick, the first thing before I even look at the exam, write down this formula sheet, those formulas that I want to help remember what they mean, right? Or label them. So that's how I would do it. I think it helps out a lot. Notice that's a tool that leads to more success on the exam. So I print that out early this week as we start working through things, start writing down next to these formulas with it. So we got this formula sheet. If we go down here, right, I've got that Poisson distribution probability mass function. I'm going to leave that up here as we work through some examples on the board, because the one I wanted to go through was, let's assume that we've got an average rate of, I'll make this one 14. Okay. So let's say we're looking at number of successes. Well, we can set the number of traffic accidents just because we need something to kind of start off with. But let's say we have got some road, we're looking over a week, and on average, we see there's 14 car accidents on this road. And we might be interested, what's the probability we see 7 car accidents this week? Well, that's one, hopefully we kind of work through similar examples, have our lambda with our x, plug them into that probability mass function, and it spits out as that answer. So a slightly more difficult one would be, what's the probability I see this random variable of, let's say, what's the probability I see 3 crashes today? We don't have the average rate of a day, I have the average rate of a week. But as long as the assumption is that car accidents are equally likely across days, which this specific example, maybe you could have a problem with that. But if we had something where across the week, every day it was equally as likely, we can change this average rate to a day, right? We can kind of adjust the time frame. So if I know that there's on average 14 accidents a week, how many on average would I see every day? 2. Yeah, 2. I was getting worried about this. If I see 14 every week, on average, every day there's 2. And so what did you do in your head there? You just kind of took your old lambda, right? And you divided it by some factor. So all this kind of your old lambda, or the more general, you'll divide it by some factor. Now what that factor is depends on, am I going from a week to a day, right? Then I divide by 7. What if I'm going from a year to a month? I divide by, how many months are there in a year? 12, right? It should be easy conversions. I'm not going to give you something that, like, if I didn't do time, right? I'm not going to do something like miles to yards. Right? I don't remember that one off the top of my head, right? So, this is going to be the process. Anytime we want to go from like a longer time period to a smaller time period. So we're going from a longer to a smaller time period. We're going to be kind of dividing by some factors. That's kind of what we do. So here, once I find my new average, right, 14 over 7 is 2. So probably I see 3 in a day. Well, now I just use my average rate for a day. So I do what? Lambda to the x. So 2 to the 3rd power times e to the negative lambda. So e to the negative 2 divided by, it's supposed to be a 3, x factorial, right? And now it's just like what we were doing before, right? Once I convert my average rate to the time period I want, well, now everything plays out just like what we were doing before. Okay? Any questions on this? Okay with this? What if I wanted to go something like, this one's going to be a little bit wild. I wouldn't actually do something like this because we'll see that the math is a little tricky, but just for the conversion factor, I'll make it a little easier. So let's say we've got, our average over a week is 14. Right? What if I wanted the probability that I see something like, I don't know, 100 over the year? Right? So now I'm going from a smaller to a kind of larger time interval, right? Going from a week to a year. My new lambda for the year would be what? Just take my old lambda, my average over a week, and do what? How could I convert the average of a week to a year? Yeah, so multiply by 2. right? I wouldn't do something like this in the exam because when I multiply by 50, this becomes a really large value. 100 factorial we can't do, but just using this for the sake of the example that when we're going to go from a smaller to a larger time frame, what we're going to do is take kind of our old lambda and multiply it by some factor to get it, right? So if we're going from a smaller to a larger time frame, multiply by your factor. You're going from a larger to a smaller, you're going to be dividing, right? And like I said, I'll keep these easy. I probably won't even do year to a month just because it does change how large it is. Usually it'd be something like days to weeks, maybe minutes to hours, right? Or hours to a day, right? So multiply by 24 there. So it'll be kind of these easy factors of time that we're all familiar with, right? And I'll probably even be real obnoxious and like put on there are 12 months in a year, or there are 7 days in a week or something, just to make sure that we're all kind of starting off on the same page. Right? This is the only other thing I would do with Poisson distribution problems is potentially give you kind of different time intervals. So you have to then think of it as update your lambda, right? Get your new average rate for this new time period. And then once you have that new lambda, everything's exactly the same. Any questions over either of these kind of ideas? So this kind of wraps up what we have for the Poisson. Don't trip over my laptop bag here. Let's look at practice exam B. So practice exam A, I originally kind of put both answer keys up there, but I uploaded another answer key that's more detailed, right? So I open this up here, and someone told me that it looked helpful. So let me see. Oh, let's go back to this section. It's going to look like this, right? Where I actually kind of have the answers worked out, how I came up with them, not just bolded the correct answer. So because we don't have that for practice exam B, that's the one that I'm going to go through in class, right? That way, you can see how these are worked through in class, and then you have that kind of Word document for practice exam A to see how you would work through those. Okay? So it starts out pretty easy. So I'm not going to start just with problem one, just because we have today and Wednesday. I think we could get through most of the problems. When it comes to things like calculating means and kind of medians here, or I guess this is a standard deviation, right? Here's the median. Those shouldn't be too tough, right? So I'm going to go down to one that I think, oh, we can do these, right? I'm going to go down to this contingency table, and we'll start working through this set of problems. So I might throw in a couple additional ones because I've got the exam printed and kind of ready to go. So I know which ones might be helpful for you to see. So I've got this situation where we've got two events I'm interested in, whether or not someone is Republican or not, registered Republican, or whether or not they want marijuana legalized, right? So we think of this as event A and A complement and event B and B complement. Right? So if we're trying to fill in this missing value for X, what did we say about contingency tables? I could have actually left these total columns off. How would you have reproduced these totals? Remember, you said it has to be true. Nobody remembers where these total columns come from? Yeah. So the totals have to add up to equal 1. But how would I reproduce those totals if I only had those top 4 left cells? I can add across the rows or down the columns, right? So I know that 0.35 and 0.1 has to be equal to 0.45. Now, the reason why is because, well, if I don't want marijuana legalized, either I don't want to legalize I'm a Republican, or I don't want to legalize and I'm not a Republican. It's every single possible person who doesn't want to legalize. That's why we can add across the rows and down the columns. So if we're trying to find X here, there's 2 ways to find it. Right? I can either look at this and say 0.15 plus X has to be equal to 0.55. So we'll start doing our work order here. So 0.15 plus X has to be equal to 0.55. Here's a little bit of algebra, right? So X, subtract 0.15 from both sides, right? And I'm left with what? 0.4. Or I could have went down the columns and said X plus what? 0.1 is equal to 0.5. Once again, we'll do a little bit of algebra and figure out X is equal. So kind of remembering that, and I could have like left a total off, And that way, I left the total off, it's almost a little bit easier because you look at, 0.35 plus 0.1 is 0.45. I just add across the rows, we're down in columns. Any questions about how we would tackle this? So what do those top 4 left cells represent? You don't have any idea what those top 4 left cells represent? Exam's going to do a rough one. What does this represent? The probability of the intersection, right, of whatever the row and column is. So the probability someone wants marijuana legalized and is a registered Republican is 0.15, right? That's how we read all those top 4 left cells, is the intersections of whatever those row and column headings are. So I think the next one that's probably, hopefully, oh, I didn't give you that one. So this one was a little bit more difficult. Maybe on the exam, I might be kind. I just simply ask you for the intersection of 2 events, which is literally just finding the correct one of those top 4 left cells. So it's not one of the problems on here, but I'm probably going to give you one like that. That should be easy points in the exam. Okay. So instead, what if I ask you something slightly more difficult, which is what's the probability that an individual wants marijuana legalized, given they are a registered Republican? So let's just first start out. I think this is always helpful to write down what you're looking for, right? So anytime we see this word given, we're looking at a conditional probability, right? So what were we given here? Well, I believe it was that the person was kind of this registered Republican. I think I even said, I'll call this event R up here, right? R is being Republican, LM would be wanting marijuana legalized, right? So given that they're Republican, what's the probability that they want marijuana legalized, right? Those are our 2 events. Okay? Well, if we can't remember off the top of our heads how we find a conditional probability, all right, I go to my formula sheet, scrolling around, I'm looking, okay, here's some conditional probability stuff. Oh, but this looks more like Bayes' theorem problems. I know that there's actually, if I have the information, a much more simple equation for finding the conditional probability. So here, if we want the conditional probability, it's the intersection of those 2 events divided by what we're conditioning on. So here, if I think about this as my A and this is my B, right? I want the probability of LM and R, right, divided by the probability of what I'm conditioning on, which is just the probability of R. So here I go back up to my table. What's the probability that someone wants marijuana legalized and is Republican? 50%, or a probability of 0.15. What's the probability that somebody is registered Republican here? Yeah, 0.55. It's just a matter of getting that entered in my calculator. I've got it. Right? So what? That's going to be just over 0.3, so 0.36. I'm guessing if we underwrite it, that's what we get. Any questions about how you kind of solve this? Yeah.
Is that 0.55 or 0.5?
Oh, did I look at it wrong? Yeah, I didn't look at it right. You're right. 0.5, which makes it a lot easier, right? Ends up being 0.3. Any other questions on how I would do it on different conditional probabilities? Now, one thing well, let me see. I don't think I do it in the next problem, so I want to point it out if I did. Oh, no, I did. This is great. So what's the probability that an individual is not a Republican and does not want marijuana legalized? Well, this is hopefully an easier one. So I've got this and, right? I'm looking for an intersection. Now, if I was writing this out, right? Because on the exam, maybe I asked you for a conditional probability that isn't one of the events, but it's its complement. Right? So maybe I say, what's the probability that someone doesn't want marijuana legalized, which would be LM complement, right? And let's say they are not a registered Republican. Now, if it helps you out in the exam, instead of writing these things as complements, you could just write like LM is equal to no and R is equal to no, right? Because I think that's kind of how the contingency table was set up, right? Instead of like using the terminology of complements, I kind of use this yes and no, right? But really the idea is a complement, right? You either are a Republican or you're not, right? not being a Republican, that is our complement. Okay? So here, this probability should be as simple as finding the intersection of those two events. All right, so we look at doesn't want marijuana legalized. It's not a registered Republican, 0.1. Okay? All right, if we're looking for an intersection, it's simply one of those top 4 left cells. Just matching it up with the 2 events that we want. Okay. Questions on that one? All right, what if I asked you instead, this one's not on this exam. It's not on the exam, there's probably a reason I'm doing it. So, what's the probability of LM or R? So that's someone either wants marijuana legalized or they're registered. So we might not recall this, but we want the union of 2 things. We said, let's simply adding the probability of each event, but then we've double counted what's in both of them. So we would subtract out the intersection. If we can't remember that, on our formula sheet, we've got that right here, right? The union of 2 events, just add up the probability of each event, subtract out their intersection. Okay. So before I go over to the other side of the classroom, right, this is simply going to be, here's my event A, here's my event B. So the probability of event A, which is that they want marijuana legalized, plus the probability of my other event, which is that they're Republican, minus the intersection of the 2. Right? So here, what's the probability someone wants marijuana legalized? 0.55. What's the probability that they're a registered Republican? 0.5. Subtract out the intersection of those 2, which is that 0.15. Wait, not 0.5. So I think this is what, 0.9. So know how to find intersections. That one's pretty easy because they're directly given to us. Conditional probabilities, a little bit more difficult, right? But the 2 components, the intersection and the probability of what we're conditioning on, those are just 2 things we can grab from that table. The union of 2 events, let's get a little bit more work. We need the probability of both events and also the probability of intersection, but all 3 of those come from that table as well. And those are really the kind of only things I can ask you for. Well, these will be the things I will ask you. And maybe solve like these missing values. Okay, if I leave one of the cells out, we should be able to either add across the rows or down the columns to figure out what that missing component is. Okay. So that would take us to 8 and 9. Okay. So 8 and 9 shouldn't be, well, especially I think it's 8. No, 9 should definitely be one that's fairly easy. Okay? So if we remember our 2 definitions of some unique things that happen, they make some of our formulas easier, but we have mutually exclusive or independent events. Mutually exclusive should be easy when we're looking at these contingency tables, because the definition of mutually exclusive was that 2 things can't happen at the same time. So if 2 things can't happen at the same time, right? We'll just use A and B for now. That means the intersection should be equal to what? 2 things can't happen. The probability of seeing them both happen at the same time would be 0. Okay. So if 2 events are mutually exclusive, we can't see both of them at the same time. The intersection of those 2 events is 0. So when it comes to looking at our contingency table, how can we tell if being a Republican and wanting marijuana legalized are mutually exclusive events? It would have to be that we see what value in that table. A 0 when we look at the intersection of those 2 things. Well, the intersection here has told us the probability of that is 0.15. So no, they can't be mutually exclusive, right? The only way they're mutually exclusive is if that intersection is equal to 0. So when we look at problem 9, we know right away that, well, I don't see any zeros in that table. So it doesn't even matter what events I'm looking at here. None of them are mutually exclusive. There's no 0 in that table. So no, they're not mutually exclusive. But then why? Well, because these 2 events, not that the union isn't equal to 0, but it's that the intersection is not equal to 0. So there would be A, right? There we're looking for the intersection of these 2 events has to be equal to 0. Well, it's not. So no, they can't be mutually exclusive. If we did see a 0 in that contingency table, well then, yes, they are mutually exclusive because the intersection is equal to 0. Which in fact here, we don't even have one that's like that, right? The two answers that are yes here, yes, because the intersection is not equal to 0, that doesn't line up. Or yes, because the union is equal to 0. We're not worried about the union at all, we're thinking about mutually exclusive events. Actually, a little more interesting, why does that last one not even make sense at all for like anything we're doing? What would it mean if the union of two events are equal to 0? If I'm in either A or B, that probability of being an A or B is 0, it means that the probability of either event is, yeah, that doesn't make any sense for anything, right? So that, if we stop and think about the possible answers here, we could have ruled out C and D, right? C didn't line up. But then B doesn't even make sense because once again, we're looking at the union. We need to be looking at the intersection to determine if they're mutually exclusive events. One shouldn't be too bad. Independence is a little trickier, right? Now we have a couple different checks for this. If I want to know whether or not events are independent, we said that's the probability of A is equal to the probability of A if I condition on B, right? That having this additional piece of information doesn't change, doesn't update my probability of A occurring at all. So in the context of our example, right, we're going to be thinking about the probability of LM equal to the probability of LM, given that we know they're registered. Well, we can check this, right? If I want to go up here, the probability they want marijuana legalized is 0.55. So here, this guy is 0.55. And then we can solve for this. In fact, I think we did it earlier. Maybe we did the other order, but right? We want a conditional probability. We said earlier, with our formula sheet, that was just the intersection of these two events. So the probability of LM and R divided by the probability of what we conditioned on, which was that the individual is Republican. I think this is the one where we had what, 0.15, and then I messed up and looked at it wrong. It actually was 0.5 in the denominator. So this was 0.3. So 0.55, is that equal to 3? Or sorry, equal to 0.3? No, right? So the conditional probability here, if we check it, it's not the same as the unconditional. So we said they're only independent if those two things are the same. So here we've got an example where no, they're not independent. Okay. So we've proven to ourselves that no, they're not independent. So we know that the answer should be no here. Right? And then I checked this a different way, but it doesn't matter. I could have checked it kind of using the probability of unconditional probability of R and the conditional probability of R, right? Either way I check it, they're always going to be independent. Right? So here what I'm looking for is, I know that they're not independent, so now either A or B is the right answer. And here I need to just check to see, is one of the events conditional probability equal to that same event's unconditional probability? I checked up here to see that probably wanting marijuana legalized was the same as wanting marijuana legalized given their Republican. But I could have also checked to see if the probability of being Republican, right, the unconditional probability of R, was the same as the conditional probability of R, right, conditioning on the other event. So it doesn't matter which way I check it, they both would have led me to believe that they're independent events. So the definition kind of here would not change, right? If LM is independent from R, it would also have to be true that R is independent from LM. Right? So we know they're not independent because those two things, in fact, aren't equal to each other. Right? So we have what answer B there. So when you're looking at these answers as well, remember, whatever is on the right-hand side of that conditional line, that's like the information you're given to be true. So this, right, we're conditioning on R, but we're still looking for the probability of whether or not they want marijuana legalized LM. So this is the conditional probability of whatever's on the left-hand side. We're conditioning what's on the right-hand side of that line, but we're still looking for the probability of whatever's on the left-hand side. Questions? Sounds a little bit tricky, right? We still have to, we kind of actually have to do a check for it. It's not as easy as looking to see is there a 0 up there in the contingency table, right? We have to kind of use that equation for finding that conditional probability to make sure that that conditional and unconditional probability aren't equal to each other, or that they are, then they would be independent. But it's not as easy as like seeing that directly in the table. And we have a little bit more work to do. Okay. Questions on anything here before we keep moving?
So did this one end up being A or B?
Right. So we said no, they're not independent, right? Because the conditional and unconditional probability weren't the same. So it doesn't matter if we're checking to see if this is true, right? The unconditional and conditional probability are, or the unconditional conditional probability are. What has to be true though is that we're looking at the conditional and unconditional probability of the same event, right? So if we're looking up here, if I look at A, well, there I've got the what? Conditional probability of R, right? I'm still looking for the probability of R, I just conditioned on LM. Well, I'm comparing the conditional probability of R to the unconditional probability of LM. That doesn't tell us, that relationship doesn't define anything for us, right? So there, that one doesn't make any sense because we're not even comparing the conditional and unconditional probability of the same event. In fact, if we look up here, that one we could rule out right away. At least the other ones, we're comparing the conditional and unconditional probability of the same event, right? So the A there is the one that doesn't make sense because we're not comparing that conditional. In fact, if you really wanted to go out even further, we could have ruled C out right away as well. Because if in fact they were independent, what would have to be true about the conditional and unconditional probability of LM? If they were independent, they should be equal to each other, right? Which is what this one's saying here. So D could make sense, right? We would still have to check it, right? We checked it, we found out it's not, it doesn't. But here we could actually rule out A and C without even checking to see if they're in fact independent. And there's a lot like that. Like we look at the possible answers here. A lot of times I think the multiple choice is helpful for you guys, even though sometimes I get a little pushback on that, because a lot of these we've already seen. You can start to rule out some of the answers. In fact, I don't know if we'll have an example today. I'll try to make sure that I look at one Wednesday. Occasionally I'll put one up there where if you just stop and think about what we can rule out, you can rule out 3 to 4 answers, right? And save yourself a little bit of time from actually using the formulas, right? I mean, it's important that we know how to use the formulas, but it's also really important we understand just the principles behind what statistics we're trying to find. Any other questions on that one? Ben? Okay. I want to save a little bit more time for these because I really want to be able to go through this example in depth. So we'll save this one for Wednesday. We'll start kind of doing some of these because they're a little bit easier. We'll get through a few before we have class. I'm not doing this for myself. I actually want you guys to, I want to be able to use our time efficiently to get you prepared for the exam. So let's say I have an example like this. We went through one that was very similar in class. In fact, might be the exact same setup, just maybe slightly different values. But I've got these different bonus amounts. I can kind of remember this example, and there's different probabilities of each one. So if I wanted to find this mean bonus amount, right, this is not as simple as adding these values up and dividing by 4, right? That would work if we had kind of a variable in our data set, and we weren't trying to make a projection for a random variable, right? So with a random variable, we've got 4 different outcomes, but they all have different likelihoods of occurrence, right? So this is where we said we're essentially going to treat this like a weighted mean, but the weights that we're going to be using are our probabilities. So we've got these different x values. I have the probability of each one first. So all I'm going to have to do is add up every single possible outcome I can see for x, multiplied by the probability I see that outcome, right? So do that for every single possible outcome and then add them all up. So here, that's what? 10 times 0.15 plus 6 times 0.25 plus 3 times 0.4 plus 0 times 0.2. Just to kind of line this up with what we're thinking about. If we had something where we couldn't remember that formula, we go to our formula sheet. Here we've got our discrete random variable of our general formulas for the mean and the variance. That one I have up there on the board, right? That was for our mean. Okay. Questions on and that one. So this is our mean of a discrete random variable here. We said it's kind of like a weighted mean, but we can ignore the denominator. If we have our weighted mean over here, because the sum of our weights, well, if our probabilities are the weights, the sum of the probabilities should just be equal to, I take the probability of every possible outcome and I add them up. Well, that covers every possible scenario, so they should add up to 1. Okay. So here I've got my variance equation for a random variable. I'm going to guess that's the next question I asked. But I do want to kind of walk you through this one a little bit because this is what I'll do in the exam to make sure that we don't have cascading errors. I think if you compute this, we should get 4.2 million. So notice the mean is 4.2. But in order to find the variance, you're going to have to look at deviations from the mean. So if you got the mean wrong, probably going to get the variance wrong, right? So to prevent you from doing that, right, I'll give you an assumed true mean in the next question. Right? So I now want you to find out the variance, the standard deviation. Right? But I need the mean, so I'm giving you all kind of assume that instead of whatever you found in the previous problem, assume what you found was 5 million. Right? So assume we found 5 here. All right, so we're all starting off in the same place. Well, right away, if I know I'm looking for a standard deviation, which one of these can I rule out right away? Yeah, B, right? I'm looking for a variance or a standard deviation, so the lowest of those can never be is 0. No variation in the data. We're out from 0. And then from there, it's just increasing. I can't ever go negative. I can't see like negative variations. So the process that we're going to use, we'll look at those deviations from the mean. We'll square those for every outcome, and then multiply that by the probability I saw that outcome first. So for here, let's see if I can remember all these guys. So the first one was 10. Subtract that mean of 5, square that deviation, and the probability I saw 10 was 0.15. Now in practice, instead of doing this all in one line, maybe like write these down in a separate column, and then you can kind of add them all up at the end. So put this in your calculator, write that number down, look at the next possible value, which is 6 minus 5, square that deviation. Well, what was the probability I saw 6 occur? In our table, that was told to us from 0.25. Go through all the possible outcomes here. Add them all up, and then we're done, right? If I add all these up, deviation squared times the probability, and I add these all up, that's going to give me the variance, right? What did the question actually ask for? Standard deviation. So the last step I would have to do is take the square root. Right now, just leave it the standard deviation. So I believe I might have reposted this one. I think originally. This one should be easy. We'll end on this. What's the probability that a trader gets a bonus of at least 3 million? Right, so that means we see the outcome be 3 million or higher. If I go up here, that's as simple as, well, the probability I see 3 million is 0.4, plus the probability I see 6 million is 0.25, plus the probability I see 10 is 0.15. So I'm just adding up the probabilities of every possible outcome that fits that criteria, right? It's really what we're doing with, like, remember when we do the binomial and we said, what's the probability I see 3 or more successes? Find the probability of 3, plus the probability of 4, plus the probability of 5, up to whatever the cap is. Same idea here. We have a smaller number of possible outcomes. Actually, that shouldn't be too bad. So on Wednesday, I'll probably start out with a Bayes theorem example, right? Those are the trickier ones. We'll probably then do some binomial stuff. And from there, if you do happen to go to the practice exams, even before I do those, I'll take questions from, if you have specific questions from any of you. Because Wednesday is really for you guys to do well on the exam, right? So I want to go over questions that you're finding difficult, right? So Wednesday, feel free to kind of come to class with questions. We'll go from there. If you need any help in those homeworks, feel free to reach out, okay?
I was gonna ask, I don't know how to find like the exclamation